You've probably heard about it. It's maybe the biggest rivalry in all of statistics, a debate that seems to pop up everywhere, from university classrooms to heated online forums.
Yeah, that's the one. Frequentist versus Bayesian. It's always presented like this epic showdown. You've got the Bayesians in one corner talking about updating beliefs in a totally coherent way. And in the other corner, you have the frequentists defending their turf with objective procedures that are guaranteed to work in the long run. It feels like a real heavyweight title fight, right?
But what if I told you that this entire fight, this whole intellectual war, is basically built on a giant misunderstanding?
This simple truth is, the debate is completely misguided. And it's not because one side is secretly right and the other is wrong, it's because they're not even in the same fight. Heck, they're not even playing the same sport. They are fundamentally answering different questions.
So, to really get this, we've got to pop the hood and look at the engine. It turns out that pretty much all of modern statistics, and that includes frequentist, Bayesian, and even a third way we'll talk about, they all start from the exact same place. There's one common engine, which then gets aimed at three totally different problems. And that engine is the likelihood function. Now don't let the notation scare you. All L of theta given y means is this. It's a way to measure how plausible our data, y, is for different possible values of our parameter, theta. We're essentially asking, hey, if the true parameter was this value, how likely would it be that I'd see the data I actually saw? The key thing to get is that it's a function of the parameter. We're testing out different thetas. This right here is the bedrock, the shared DNA for everything that follows.
So once we have this powerful tool, it lets us ask our first big question. This one's all about pure, unadulterated evidence. If we strip everything else away, no prior beliefs, no long-run guarantees, what does this specific pile of data tell me?
This is the world of R. Fisher and the likelihood approach. And here, evidence is always comparative. Use the likelihood to create a ratio. You're not asking for an absolute truth, you're asking, how much more does the data support parameter value 1 compared to parameter value 2? Is it twice as supported? 10 times? 100 times? It's all about the relative strength of evidence.
And that was the entire game. The goal here isn't to tell you what to believe or what to do next. It's just to be a neutral scorekeeper for the evidence contained in this one data set. That's it. Nothing more, nothing less.
Okay, but sometimes just knowing the evidence from one experiment isn't enough, right? You might need to ask a totally different kind of question. Imagine you're developing a drug or a manufacturing process. You need methods that you can trust to work reliably, over and over and over again. You need procedures with guaranteed error rates.
And this is the heartland of the frequentist.
Let's look at the famous confidence interval formula. That probability, that 95% or whatever, it's not about theta. From a frequentist point of view, the parameter theta is some fixed, universal constant. We just don't know what it is. The thing that's random here is the interval itself, the Ci of y. Because if we got different data, we'd get a different interval. The probability is about the procedure.
So let me be super clear, because this is the single most common misunderstanding in all of statistics. A 95% confidence interval does not mean there's a 95% chance the true parameter is in the interval you just calculated. No, it means the method you use to build the interval will successfully trap the true parameter 95% of the time if you could repeat your experiment forever. It's a guarantee about the quality of your tool, not a statement about this one specific result.
All right, on to our third and final question. And this one is a massive philosophical jump. We're leaving the world of abstract evidence and long-run guarantees behind. This question is personal. It asks, based on what I thought before and the data I just saw, what should I believe right now?
Well, this is the exclusive domain of Bayesian inference, all powered by the beautiful Bayes theorem. Look at what it does. It takes the likelihood, P of y given theta, which is what the data is telling us, and it combines it with our prior belief, P of theta, and what comes out the other side is our updated belief, our posterior probability, P of theta given y. The probability statement is now directly about the parameter itself.
So you see, in the Bayesian universe, the parameter theta is treated as a random variable, precisely because we are uncertain about it. Probability here is the language of belief, and we take the data we actually saw as fixed, and we use it to update our beliefs. The end result is a statement like, given the data, I am 95% certain the true value is in this range. Sound familiar? It's what people think a confidence interval is telling them.
Okay, let's put this all together. This table right here, this is really the whole story. Three distinct frameworks. All start with the likelihood. but they treat different things as random, they define probability differently, and they give you completely different kinds of answers. The likelihood school gives you relative evidence. Frequentism gives you error guarantees, and Bayesianism gives you an updated state of belief.
So you see, it was never a fight. It was a conversation where everyone was talking past each other. They all use the same math engine, but because they are asking fundamentally different questions, they are of course going to get different answers. It's not a conflict, it's just different goals.
So if it's that simple, then why does this fight just keep going? Well, it's because of a very common glitch in our thinking, what philosophers call a category error. We keep grabbing a tool from one toolbox and trying to use it for a job it was never built to do.
And here is the absolute classic example. On the left, you have the proper frequentist statement for a confidence interval. This procedure I'm using works 95% of the time. It's a guarantee about the method. But on the right is how it's almost always misused, as a Bayesian statement of belief. I'm 95% sure the true value is in this specific interval. You're asking a frequentist tool to give you a Bayesian answer, and it simply can't do that.
This really gets to the core of it. The problem isn't that p-values are broken or confidence intervals are useless. The tools themselves are perfectly fine. They only fail when we misunderstand them, when we try to use a tool designed for long-run error control to tell us what to believe right now.
So, what about the people who actually have to get stuff done? You know, the analysts in the trenches. The unspoken truth is that in the real world, serious practitioners couldn't care less about these philosophical wars. They are pragmatists.
Yeah, applied statistics is all about using the right tool for the right job. A good analyst has a whole toolbox. They'll use likelihood methods to just explore the data and see what's going on. They'll use frequentist ideas for quality control to check if their models make sense. And when they face a really complex decision that involves uncertainty and prior knowledge, they'll reach for Bayesian models. It's about being effective, not being ideologically pure.
So if you only take one single thing away from this explainer, please let it be this. The next time you see a statistic or you have to solve a data problem, do not start by picking a team in some imaginary fight.
Always, always start with the question, what are you actually trying to do? Are you trying to weigh the evidence? Are you trying to control errors in the long run? Or are you trying to update your personal state of belief? Once you are absolutely crystal clear on the question you're asking, the right framework and the right math will just fall into place.
You know, if this helped clear things up for you, I'd really appreciate it if you'd like this explainer and subscribe for more content that's all about bringing clarity, not starting arguments. And remember, before you ever accept a statistic, the most important thing you can do is fact-check the question it was trying to answer in the first place. A huge thanks for watching. This explainer was made in partnership with the sharp minds at Stat Harbor Analytics.